Good afternoon, everyone, and welcome to the second Brookhaven Lab Research Slam competition. So my name is Sharon Pepinella, and I am the Senior Research Programs Representative for the Office of Educational Programs and the MC for today's competition. Over the past few months, 10 postdocs and early career professionals across 8 different B&L departments have developed, practiced, and fine-tuned 3-minute talks about their research designed for a general audience. I would like to thank the participants for their hard work, patience, and perseverance in developing these talks, as it is no easy feat. Each of these contestants have had their talks dissected, often numerous times, by scientific, communications, and educational experts. However, we hope they found this to be a rewarding experience, as these participants now have the opportunity to highlight their impressive research for you and have further developed their skills to communicate their research with a non-specialized audience. At this time, it is my pleasure to introduce David Manning, who will deliver a brief welcome address.
I'm really excited to be here. So we love our science in 3-minute components. And my real role today also, though, is to thank Sharon and Aleda, Karen. There's a tremendous group in stakeholder relations who really appreciate the effort that you all have put into this. We have an amazing internship program. We're very focused, and you know, John knows this, on the elements of this laboratory which are so critical, which is encouraging young scientists and young employees. And that's, I think, our greatest pride. So I have to tell you that really one of the highest rated educational program offices in the entire laboratory system is here at B&L. We're ferociously proud of that. We have a very small group that work very, very hard. So the fact that you've all devoted your time to this and will give us this moment of joy is very much appreciated. So thank you to all of the contestants. Thank you, John, for the support. And thank you to OEP for all the work. Thank you.
Thank you, David. Before we jump into the talks, I want to extend my sincerest thanks to laboratory leadership for their continued support of this event. I also want to extend a special thank you to Joe Gettler from Stakeholder Relations, who's worked closely with me both last year and this year to help bring this SLAM competition to fruition. I also would like to thank Tom Kubley from CAD and last year's SLAM winner, Daniel Marks from EIC, who has provided valuable insights for our participants during our SLAM practice sessions. Of course, a big thank you to our panel of judges for recognizing the value in this type of event and for taking time out of their incredibly busy schedules to participate. And I'll speak more about our judging panel in just a moment. We also appreciate the scientists, supervisors, staff, mentors, everyone who has supported our participants' research and helped them to refine their talks. And of course, a big thank you to Aleda Perez and the Office of Educational Program staff, without whom this competition would not be possible. Okay, so I just want to give you a little bit of information about what it is our participants are competing for. There are cash prizes here. So first place winner will take home a lovely $2,000 check. Second place, $1,000. Third place, $500. And there is a people's choice. What that means is you, the audience, get to select someone to take home this award. I'll explain more about that a little bit later, but you'll see on the agendas that you received coming in, there is a QR code. I will also post it at the end of the talks. That will open at the end of the last talk, and you can make your votes until 2:50 p.m. Additionally, one of our 3 winners will be selected to move forward to the National Lab Research Slam competition, where 1 individual from each of the 17 DOE national laboratories will compete on Capitol Hill in Washington, D.C. in front of congressional delegates. So that is an exciting honor. Some information about our 2024 judges. We are very excited to have John Hill, our Deputy Director for Science and Technology, Mary Rogers, Small Business Liaison Administrator, Lisa Miller, Senior Biophysical Chemist, Karen McNulty Walsh, Principal Media and Communications Specialist, and Aleda Perez, Interim Manager for the Office of Educational Programs. As you can see here, we have a fantastic mix of leadership, scientific communications, educational expertise across the board, really the people that you want to be judging a competition. Some criteria that the judges were provided, so this is what they're going to be looking out for. Presentation of background and significance of the research, clear logical sequence, enthusiasm, avoidance of scientific jargon, the speaker's ability to capture and maintain audience attention, stage presence, and of course, appropriate use of the allotted 3-minute time. And I'm going to jump back because I definitely missed a slide. So, what is it that you were looking at? So these SLAM talks, as mentioned, are 3-minute talks about these contestants' research. So this is a bite-sized nugget of what they do, and it has to be accessible for a general audience, so non-specialists. After each of the 3-minute talks, there is going to be audience trivia. So we have both a mix of trivia related to Brookhaven National Laboratory, and because it is December, we have 2 trivia questions this year, 1 B&L and 1 holiday-related trivia. So you, the audience members, will have the opportunity to win a prize if you answer correctly. What will happen during the trivia is I will read the full question and all 4 of the multiple choice answers. Please do not raise your hand before I read the last multiple choice answer. In the back, we have Tina and Cindy, who will be looking for the first person to raise their hand at the end of reading the answers. And if you get the correct answer, you get a Brookhaven National Laboratory water bottle. I know, good stuff. So at the completion of all of the talks, you are invited to a reception out in the lobby. So the reception will be from about 2:30 to 3 o'clock p.m. During this time, the judges will deliberate, and we will identify our winners. You will also then be able to do your People's Choice selection for your People's Choice vote. After that, you are all invited back here at about 3 o'clock p.m. for the awards ceremony to see who our winners are. And with that, let's jump to our first speaker. So our first speaker today is John Banovitz from Instrumentation. John's hobby is actually collecting hobbies, which include crocheting, woodworking, and cooking. However, his greatest love is reading, and he's only 450 books short of a library. Now, John, I looked this up, and supposedly a library is 500 books. So I think you've got a little bit of ways to go. We're going to take up a book collection after the slam. Get John there. Okay? So today, John will be telling us what you need to know about the world's largest camera. Please welcome Dr. John Banovitz.
Detect millions of stellar explosions, and possibly even find new exoplanets. In order to do this, we're going to need a very impressive camera. And for a survey of this magnitude, we'll need not only a large camera, but the world's largest camera. Now, this camera is about the size of a small car and includes many different systems, including the world's largest lenses and filters, over 200 light-detecting sensors, an electronics and refrigeration system that needs to cool these sensors down to negative 150 degrees Fahrenheit. My work is to commission and characterize these systems, specifically focusing on the sensor system that was developed here at BNL. To do this, I shine light of different wavelengths on these sensors that represent the 6 different filters that will be used in the survey. This is to determine what sensor effects happen at different wavelengths of light, how much light can a sensor take before it begins to misbehave, and to identify individual defective pixels out of the 3.2 billion pixels that we have with every image. We need to integrate, calibrate, and commission all these systems so that each individual image is as perfect as it can be. So at the end of the 10 years, we can confidently say that we captured the cosmos.
Thank you, John. It's trivia time. Our first question is a Brookhaven National Lab related question. We have Cindy in the front. Remember, you cannot raise your hand until I finish reading all of the 4 multiple choice options. So your first question is, Brookhaven Lab is a U.S. Department of Energy site. Several other government agencies also have locations here on site. Which of the following is not one of them? A, the U.S. Postal Service. B, the U.S. Patent and Trademark Office. C, NASA. Or D, the National Weather Service. I think right here in the light-colored shirt, from my view, yes.
B, the Patent and Trademark Office.
B is correct, the U.S. Patent and Trademark Office. And they get a little tougher. Our second trivia question. Which of the following holiday movies was not developed with claymation animation? Is it A, Rudolph the Red-Nosed Reindeer? B, The Year Without a Santa Claus? C, The Nightmare Before Christmas? Or D, Frosty the Snowman?
C, The Nightmare Before Christmas.
That is incorrect.
Boo, Jaw.
B.
B is incorrect. By the way, I'm also going to remind you, if we get 3 wrong answers, I get the water bottle.
It is D.
D is correct, Frosty the Snowman. Thank you, Cindy. Okay, our next speaker is Yu Dai from the biology department. As a child, Yu believed she could talk to plants, which I imagine would be a valuable skill now that she studies them. She also treats every day like a mini adventure because there's always something new to discover if you pay attention. Today, Yu describes plants under pressure, cracking the code of adaptation. Please welcome Dr. Yu Dai.
Most of you have probably tried to grow plants before, and I bet for many of you, they maybe end up dying. But actually, it's not fair for us to take all the blame for that, because keeping plants alive is not easy. They're confronted with so many environmental challenges every single day. Droughts, heat waves, flooding, and also viruses, bacteria, and many other pathogens. And unlike us, they can just move to safety or put up physical defenses like we do. And nowadays, as in a changing climate, their struggle is only becoming more severe. DOE has invested substantial resources and billions of dollars in developing crops for biofuels and bioproducts. Wouldn't it be a terrible loss if these plants were unable to survive in a future climate scenario or pathogen pandemic? To discover sufficient ways to protect bioenergy crops, my research focused on understanding a fundamental mechanism that controls plant defense and immunity, which is like a control system inside living organisms that switch genes on or off in response to their environment. It's called gene regulatory network. We can imagine it as a big, complex circuit system which contains tens of thousands of elements, much like a computer CPU. For example, when a virus attacks, this network is reprogrammed to switch defense genes on and growth genes off to help the plant to adapt and survive. In my study, I'm using an experimental platform based on living cells isolated from plant tissues. The beauty of this system is that it can be easily treated with environmental stresses over a short period of time. And its gene regulatory network is easy to be manipulated. So generally, I start from giving inputs such as virus infection or the manipulation of one element. And then I can measure the outputs, such as the changes in RNA, DNA, and protein. And another advantage of this live cell system is that it allows us to measure changes over time. So I can get a dynamic view of how this gene regulatory network is reprogrammed under specific conditions. By doing so, I can discover essential elements required for this network, so we can re-engineer bioenergy crops to strengthen their immunity, better equip them for future challenges. So, in a world that's getting tougher, my goal is to help plants become tougher too.
Thank you, you too. Okay, trivia time again. In 1968, two Brookhaven Lab researchers published the first paper on this mode of transportation. Is it A, magnetic levitation, B, schwababam, C, hydrofoil, or D, Shinkansen?
The answer is A.
A is correct, magnetic levitation. I had to look up how to pronounce B, and I'm still pretty sure I got it wrong. No, yeah, that's once. Okay, our holiday trivia question. What is the name of the 9-branched candelabrum used during Hanukkah? Is it A, the kinara, B, the taper stick, C, unity candle, or D, the menorah?
It is D, the menorah.
Menorah is correct. Okay. Our next speaker is Amy Dobracki from the Environmental and Climate Sciences Department. Amy was married in Las Vegas by Elvis, which I can personally relate to as Elvis performed my vow renewal just 3 weeks ago in Vegas. Amy has also flown over 500 hours on a NASA aircraft measuring the chemical properties of African wildfire smoke over the Southeast Atlantic Ocean, which I cannot personally relate to. Today, Amy is sending up smoke signals, how wildfire particles impact our climate. Please welcome Dr. Amy Dobracki.
I want you all to take a deep breath. Inhale and exhale. In that single breath, you just inhaled over 1 million particles. In fact, on a normal day like today, you'll probably breathe in about 10,000 times that amount by the end of the day. As an atmospheric scientist, I refer to these tiny particles as aerosols. And no, I'm not talking about the kind that come from a hairspray can. I'm referring to the ones that come from dust storms, vehicle exhausts, and wildfires. Aerosol particles are generally too small to be seen with the naked eye, but we're sometimes reminded that these particles exist in our atmosphere. Do you remember last summer when the Canadian wildfire smoke engulfed the east coast of the United States? Yeah, a lot of us remember that historic event. And even though these particles are small, they have big impacts on human health and Earth's climate. I study how aerosols impact Earth's climate by focusing on the chemical and physical changes that occur as these aerosols are transported long distances. For example, if I were to follow that Canadian wildfire smoke from Quebec to New York City, its size, shape, and chemical composition would look drastically different in Canada than it looked in New York. This research is important because aerosols are essential for cloud formation. Without them, there would be no clouds in our sky, and that would make Earth a pretty miserable place to live. However, as the aerosol properties change, their ability to form clouds changes too. And these processes are still not well understood. At BNL, we study wildfire particles both in the field and in the lab. Fieldwork provides valuable real-world data, but it doesn't allow us to systematically investigate the processes we care about. That's why I recreate these smoke particles in the lab. Don't worry, I haven't burned down the lab yet. I also recreate the environmental conditions so I can study the aerosol properties along every stage of their journey, from freshly emitted particles to particles that have been traveling in the atmosphere for a few days. Our studies show that most smoke particles evaporate and shrink after a few days in our atmosphere. As a result, the remaining particles are less effective at forming clouds, and they become more absorbing of sunlight. Aerosols and their cloud interactions can have a warming or cooling effect on Earth's planet, and depending on the strength of these processes can tip that balance. And tipping that balance can drive events like extreme weather, rising sea levels, and ecosystem disruptions, events that will not only impact our environment, but also human health. By understanding how even the smallest particles behave, we can build a more resilient future, and it starts with one particle at a time.
Thank you, Amy. Ready, Cindy? I'm ready. Okay, it's trivia time. James Robertson and Brookhaven Lab Associates built the head shrinker in 1961, the first device for which of the following techniques? Is it A, positron emission tomography, B, magnetic resonance imaging, C, nuclear magnetic resonance imaging, or D, computed tomography scan? A lot fewer hands this time.
Is it B?
B is incorrect.
I'm going to make a stab at A, PET.
A is correct. Also known as a PET scan. Okay, time for our holiday trivia question. What colors are the candles of Kwanzaa? Are they A, black, red, and green, B, black, red, and yellow, C, red, gold, and purple, or D, blue, white, and silver?
That's A, black, red, and green.
A is correct. Okay. Our next speaker is Chandima Fernando from the National Synchrotron Light Source 2. Chandima loves to travel and wishes he had studied physics in college. I feel you. Today, Chandima is going to inform us how robots drive science. Please welcome Dr. Chandima Fernando.
Robots are literally taking over the National Synchrotron Light Source 2, and that's in a good way, and my team is behind it. Let me tell you how we use robotic technologies to increase the efficiency by twofold while saving 12 hours per day for the scientists. At the National Light Source, we generate really bright, intense beam of light that is 10 billion times brighter than the sun. Scientists all over the world aim this bright light at different materials to uncover the mysteries hidden beneath them. Batteries are studied to extend their lifeline, and biological cells are studied to detect cancer at the early stages. Asteroid samples are studied so that they can uncover the origins of life. These experiments happen at closed and large chambers. However, when an experiment needs to be done, a scientist has to manually access these chambers and change these samples. This manual process is a waste of time, as we can get more science done with this light beam. This process may end up breaking the samples because of the human error. This process is a waste of scientist time. Imagine a scientist has to be there when an experiment ends at midnight in order to change the sample. Therefore, my work with robotic technologies provide a solution that increases the efficiency by twofold, does not involve any human error, and let the scientists sleep at night so that they can get more science done. We use a robotic arm to autonomously pick up samples and place in front of the light beam. This is a very challenging task because these experimental chambers are full of very expensive research materials and research equipments. So how does a robot know to avoid all these obstacles and place the sample at the correct place? Well, I give robot eyes. That is, I connect a camera to the robotic arm so that the robot can see the environment. How does the robot know to pick up the correct sample holder? Well, I tag each of these samples with a unique tag so that the robot looking at these samples from the camera not only distinguish each sample differently, but also calculates the distance between the robot and the sample so that the robot can move and get these sample holders. We are on the way to implement these changes at the light source, and our preliminary results are very promising. Well, yes, the robots are coming, and they're coming to help you in science.
Thank you, Chandima. It's go time. Okay. This question was a stumper last year, so I brought it back. What is the largest Office of Educational Program community event? Is it A, the Science Bowl, B, maglev competition, C, science fair, or D, the bridge building competition? I see it's still a stumper.
Say D.
D is incorrect.
No? Did you have?
Yeah. Is it A?
Science Bowl is incorrect.
Oh. He keeps raising his hand. I'm going to skip him.
Guess and say maglev?
Maglev is incorrect. So I will take my water bottle, Cindy. The correct answer is science fair, which means we're going to have to blast you with science fair news moving forward. This question's coming back next year. Everybody remember. All right, our holiday trivia question. Referenced in a popular holiday song, this traditional Christmas dessert recipe includes figs, walnuts, cinnamon, and nutmeg. Is it A, pfeffernuss? That one I did know how to pronounce. B, figgy pudding. C, Yule log. Or D, baked Alaska? I saw a very confident hand over there.
I'm going to go with B, figgy pudding.
B, figgy pudding is correct. Okay. Our next speaker is Arafan Islam from the chemistry department. Arafan was the first person in his family to receive a PhD and recently became a father of a baby boy. So congratulations all around. Today, Arafan is driving the catalyst for a sustainable future. Please welcome Dr. Arafan Islam.
What do factories and cows have in common? They are great. They are great at releasing two most powerful greenhouse gases, carbon dioxide and methane. These emissions raise a serious concern globally because they disrupt our environment, our habitat, our way of life in this planet. So how do we keep running our industrially important processes without harming the planet? Exactly, that's where my research comes into play. Here at Brookhaven National Lab, I am working on designing a next-generation catalyst. Think of them as matchmakers for molecules. They can make chemical reactions happen at a faster rate and at the same time efficiently. Using affordable materials like copper and magnesium, we are designing next-generation catalysts that can capture and convert these emissions and turn them into valuable chemicals, such as liquid fuels and other chemical feedstock. Now, the question is, what's the scientific problem here? Both carbon dioxide and methane are stubborn molecules. They are notoriously difficult to break down because they have strong chemical bonds. But I have a solution. Recently, we have discovered a way to activate both carbon dioxide and methane at room temperature. So when magnesium and copper reacts with oxygen, they make oxide. by bringing tiny, minute magnesium oxide and copper oxide particles into contact, we can create a hotspot. At this hotspot, the magic happens. At this hotspot, both carbon dioxide and methane can activate at room temperature, dissociate into molecular fragments, and those fragments then can react with each other to make valuable chemicals, such as alcohols, liquid fuels, and other chemical feedstock, which are easier to use, easier to handle. Those chemicals can either be recycled back to the same process, or they can be repurposed in other ways. Now, think about a future where these emissions are recycled endlessly, offering a closed carbon cycle and net zero carbon emission. We are not far from that future. Thank you.
Thank you, Arafan. Okay, you've got this. Last time was, question. We're good. We're going to move forward. Okay. The National Synchrotron Light Source 2 generates intense light beams that are how many times brighter than that of Earth's sun? Is it A, I heard that sigh, 500 million, B, 10 billion, C, 100 billion, or D, 1 trillion? Once again, a very confident hand.
B.
B is correct, 10 billion. This is why we need those robots. All right, holiday trivia time. Approximately how many cranberries are needed to make 1 can of cranberry sauce? Is it A, 50, B, 200, C, 350, or D, 1,000? Now everybody's thinking about how big those cans are right now.
A, 350.
350 is incorrect.
B, 200.
200 is correct. I'm still shocked that they can fit 200 cranberries in there. And also, no one can convince me otherwise. The jellied cranberry that comes out in the shape of the can is the best, not the whole berry stuff. We can argue later over the reception. Thank you, Joe. This is why Joe and I work together on this. Okay. Our next speaker is Ji-hee Kim from the physics department. Ji-hee embraces her Korean heritage with her absolute love for kimchi. She cannot live without it. She has also found that she is weirdly good at cornhole, so maybe we should look into a B&L league. Today, Ji-hee is detecting the secrets of matter at the Future Electron-Ion Collider. Please welcome Dr. Ji-hee Kim.
Everything around us, the chair you are sitting in, stars above, even you, it's all made of atomic nuclei, the tiny particles called protons and neutrons. And inside them, the quarks and gluons, which are even smaller. Even though these particles are everywhere, there's just so much we don't understand about how they work, especially when it comes to how the quarks and gluons behave and interact with each other, and then why the proton mass is far greater than the sum of its parts. So this is where the Future Electron-Ion Collider, or EIC, comes in to answer these questions. It will be built over the next decade at the Brookhaven National Laboratory here, in the partnership with the US Department of Energy and the Thomas Jefferson National Accelerator Facility. So EIC will be a cutting-edge particle accelerator that smashed electrons into protons and atomic nuclei. And this machine, paired with the special detector, will allow the scientists look inside the protons and neutrons to see the quark and gluons with more detail than ever before. So scientists are already working on one detector called EPIC. It will help gather the crucial data about particles and forces that make up matter. And then I'm on a team that is developing a plan for the second detector. So almost all collider ever built is at least 2 complementary detectors to cross-check and then verify for the scientific discoveries. Specifically, I'm studying how designing the second detector could enhance the accuracy of our measurement, at the same time investigate the unique capability we can offer. And then we optimize the detector baseline to reduce the background and then increase the precision of our measurement. Ultimately, the EIC will be giving us the whole new way to explore the building blocks of the universe, and it will help us to unlock the deepest secret of the matter itself, and then gain the new insights into how everything around us work. And as I mentioned earlier, the proton mass is far greater than the sum of its pieces. Similarly, the discovery from the one detector and another will be much, much greater.
Thank you, Jihi. Okay. Speaking of the EIC, the growing collaboration for the electron-ion collider includes 300 scientific institutions from how many different countries around the world? Is it A, 11, B, 15, C, 28, or D, 40?
C, 28.
28 is incorrect.
B, 15.
15 is incorrect.
40.
40 is correct. We double-checked that impressive stat yesterday, because those numbers keep changing. Okay, holiday trivia time. Approximately how many reindeer reside on site at Brookhaven National Laboratory? Is it A, 100, B, 150, C, 200, or D, none of the above?
D, none of the above.
That is correct. There are 0 reindeer on site at Brookhaven National Laboratory. That was to trick you. I would have had to, yeah. Our next speaker is Utali Lee from Condensed Matter Physics and Materials Science. Even though Utah was born after GPS, he can still drive with just a Rand McNally Road Atlas, which in this day and age is very impressive. Utah also really loves deciphering ancient languages and provided me with a lovely word as it was pronounced in the year 524.
That's my name. Yeah.
Is it?
Yes. It was called New Delve 115 years ago, but that's fine.
I was going to say, you're going to have to ask him during the reception because I couldn't pronounce it. I don't study the ancient language. So that's lovely. Thank you. Utah's talk today focuses on Autolab, AI-powered assembly of atomic layers. Please welcome Dr. Utali Lee.
When I was a kid, everything in science seemed so fun, cool, and futuristic. Now, I'm an architect of two-dimensional or 2D materials, composing of only one or a few layers of atoms. They can be stacked on top of each other in millions of ways. In principle, you can specify the exact element of each atom in a solid. This is an enormous power yet to be fully harnessed. But for most of us working in a wet lab, our daily job is often manual, slow, and boring. Because we deal with materials that are discovered only 20 years ago. The physical and the computation infrastructure necessary to manipulate them efficiently are not ready yet. After 7 years of working with 2D materials, I got bored of spending 60% of my time searching, documenting, and assembling their pieces manually. In addition, everyone is missing out on the possibilities of faster computer chips and better medical sensors afforded by 2D materials, largely due to the automation deficit in science. That is why I pioneered the Autolab project, whose core mission is minimal human intervention. The user designs a 2D material architecture in a computer-aided design program. Think AutoCAD, but tailor-made for 2D material purposes within 15 mouse clicks. Then the user goes for a coffee break while the machine builds up the sample. No need for us humans to babysit this machine. What enables this magic? AI-powered computer vision deployed on a commercial cloud platform, which is used to analyze the images of 2D material flakes. My algorithm is smart enough to see those non-uniformities as thin as one atomic layer, ensuring the best sample qualities. The robot hardware combines the flake scanning and stacking components into one, minimizing the numbers of moving parts, making the entire system lightweight and robust. Autolab has generated 3 patent applications for BNL, but still an ongoing project. The same design principles can be extended to other aspects of physical science research, such as scanning probe microscopy. I envision a not-too-distant future where scientists produce more replicable science with less repetitive labor in a manner much more relatable and convertible into industrial production than handcrafting. Goodbye, the manual stone age of science. Hello, Autolab.
Thank you, Utah. Okay, this is also a returning question because it stumped people last year. So, the Long Island Solar Farm, located at BNL, can provide electricity for roughly A, 1,300 households, B, 2,900 households, C, 3,100 households, or D, 4,500 households.
B.
B is incorrect. D. Oh, D, sorry. D is correct. I guess I won't include that one again next year. Okay, holiday trivia time. On this date, known as Krampusnacht, the legendary creature Krampus is said to visit households throughout Central Europe to reward good children but punish misbehaving ones. Is it A, November 1st, B, December 5th, C, December 24th, or D, December 31st? Get a couple really confident hands here.
B, December 5th.
December 5th is correct. Our next speaker is Lijou Philip from Instrumentation. Recently, Lijou started learning the piano, but only after midnight, hiding in the garage after his toddler is asleep. So today, Lijou has emerged from his garage to take a peek at 14 billion years. Please welcome Dr. Lijou Philip.
Thank you. 14 billion years. About 14 billion years ago, the universe emerged from a hot, dense sea of matter and energy. And as it expanded and cooled, it formed stars, galaxies, planets, basically everything that we observe today. But the timeline between when the universe began and what we observe today is huge, but it has gaps that we don't yet fully understand. For instance, there was a period in the history of the universe when there were no sources of light, no stars, no galaxies, and it was completely dark. So we call it the Dark Ages. And soon after, the first stars lit up the universe. So we call it the Cosmic Dawn. So these milestones, such as the Dark Ages, the Cosmic Dawn, are well understood in theory, but they're not observed yet. I have a background in astronomy, and my job at BNL is to design instruments to study these unexplored eras in the evolution of the universe. So how do we do this? We build telescopes very powerful enough to look back deep in space. And the signals that come from deep space are very weak. So this is one of the challenges. On top of weak signals, these signals are contaminated by all other signals that are around us. For example, man-made signals from the FM radio, televisions, cell phones, even the power tools that we use completely power these signals and make it undetectable. So what do? We build our telescopes and take them to remote locations, such as faraway islands, deserts, miles and miles away from human civilization. One of the experiments that I'm working on is putting a telescope on the far side of the moon, because this location is permanently shielded from the Earth and is radio quiet, meaning there is no human interference. So these remote locations provide us with clean data that we can look at, observe, process, and analyze for better results. And these results will help us fill the gaps in the evolution chart of the universe, which may shine new light upon new physics that we need to understand, and at the end of the day will tell us more about the fundamental nature of the universe and our place within it. Thank you.
Thank you. Okay, trivia time. Researchers at Brookhaven National Lab and Stony Brook University built the nation's longest quantum network. How many miles does it span? Is it A, 25 miles, B, 42 miles, C, 98 miles, or D, 147 miles? Oh.
D, 147.
D is incorrect. "98 miles" is correct. In total, how many gifts were given in the 12 Days of Christmas song? Was it A, 12, B, 144, C, 364, or D, 502? Oh yeah, who's good at math?
B.
B is incorrect. 12 is incorrect. Got one more guess.
C.
What was it?
C.
C is correct. It's a very expensive song. Our next speaker is Iiro Umaka from the physics department. Growing up, English was Ijiro's favorite subject, so she's still unraveling the mysteries of how she got into physics. And when you figure it out, let Chandima know. She also considers herself to be a great guitarist, at least in the rock band game. Today, Iiro is jetting through the Big Bang's soup. Please welcome Dr. Iiro Umaka.
Ever wished you had a time machine? If you had one, where will you go? Well, as a high-energy nuclear physicist, I can tell you that we're interested in the stuff of our baby universe, about 1/1,000,000th of a second after the Big Bang. The stuff of our baby universe was a hot soup of quarks and gluons known as a quark-gluon plasma. And it's from this soup everything we see around us, including you and I, came from. The relativistic Heim collider, or RIG for short, located here at BNL, allows us to make this soup. In fact, it was with RIG we made it for the very first time. The challenge about studying this soup in the lab is that it only lasts for fractions of a trillionth of a second. Now, there are no man-made probes fast enough to image this. However, nature has been kind to us. Accompanying this soup are high-energy probes called jets, generated as part of the collision. They zip through the soup, allowing us to see inside it. Now, the experimental data has shown us that this soup exhibits collective behavior, like the response of a school of fish to external stimuli. However, on a fundamental level, we know that the interactions of quarks and gluons are more like molecules in a gas. So these quarks and gluons shouldn't really care about what your neighbors are doing, like the school of fish example. This implies that our current probe is too coarse. Fortunately, we can fine-tune our probe with a lot more data. To this end, I and a group of scientists constructed a detector at RIG known as S-Phoenix. It's a state-of-the-art jet detector, 3 stories tall, and first of its kind at RIG. It will record several millions of these jets, which will provide a fine-grained probe of this soup, allowing us to study its microscopic nature. Now, the force which governs matter at this scale, the strong force, is the least understood of the 4 fundamental forces of nature. It binds the quarks and gluons within the proton and the proton within the nucleus, and thus keeps us, the stars, and the planets intact. By probing the inner workings of this soup, we're shedding light on this force. When we understand, on a fundamental level, what binds everything together, we can unlock the secrets of the tiniest building blocks of matter that made us and the vast universe we call home. Thank you.
Thank you, Iiro. Speaking of quark-gluon plasma, the quark-gluon plasma is the hottest matter to ever be created in a laboratory. What temperature is this perfect liquid? Is it A, 4,000 degrees Celsius, B, 4 million degrees Celsius, C, 4 billion degrees Celsius, or D, 4 trillion degrees Celsius? No.
Is it 4 million degrees Celsius?
4 million is incorrect.
C, 4 billion.
4 billion is incorrect. One more guess.
D, 4 trillion.
4 trillion is correct. Very, very hot. All right. Which U.S. state holds the record for the most snowfall over a 24-hour period? Is it A, Colorado, B, New York, C, Minnesota, or D, Alaska?
C, Alaska.
Did you say Alaska? Alaska is incorrect. I know, shocking.
B, New York.
New York is incorrect. One more.
Yeah, I guess A, Colorado.
A, Colorado is correct. And because I know someone's going to ask, it was 76 inches in 1921 in a 24-hour period, but Colorado also holds the record for the amount of snowfall in a single day, which was 63 inches in 1913. Our final speaker today is Shi Yu from the Computational Science Initiative. She likes to say that he trusts scientists to guide his machine learning models, but secretly, he thinks the models are the scientists. They just happen to be a bit more stubborn during training. She loves coding and dreams of accelerating scientific discovery through machine learning, because who knows? Maybe the next Nobel Prize will go to an algorithm he helped create. Today, he's building a partnership between scientists and artificial intelligence. Please welcome Dr. Shi Yu.
Creating the partnership between scientists and artificial intelligence. This idea goes beyond just a new technology. It's about working together, building the trust, and finding harmony between human expertise and AI capabilities. Scientists bring a wealth of specialized knowledge, but often struggle with analyzing a massive data set or uncovering patterns efficiently. Recently, large language model ChatGPT demonstrated remarkable problem-solving and reasoning capabilities. How can we create a meaningful collaboration where the expertise of scientists and the analytical power of AI come together to enhance each other? My research focuses on creating a flexible framework where AI is not just a tool, but a true collaborator that learns directly from humans' feedback. The goal is to develop an intuitive interface that guided the existing portrayal model to understanding the language in scientific field, like X-ray microscope images or time series data. By integrating the domain expertise and feedback, this framework transforms AI from a black box into a trust and insightful partner. Our framework lets scientists activity-guided AI, helping it to adapt to new challenges and refine its results. For example, scientists were able to guide AI to analyze the plant cell structure in X-ray images by sharing their own expertise in text, even though AI had never seen such kind of data before. This highlights how this framework helps AI to analyze the new challenges and refine itself. This is just the beginning. Building the partnership between scientists and artificial intelligence requires ongoing efforts. But the reward is significant, accelerating the scientific discovery. The vision is clear. In the future, scientists and AI work hand by hand, driving breakthroughs that shape our world. Thank you.
Thank you, Shi. All right, it's our final set of trivia questions. So if you've been jonesing for that water bottle, now's your time. Summer 2024 saw a record number of applicants for the SULI and CCI internship programs at Brookhaven National Laboratory. Now, these are not the only internship programs that OEP holds appointments for. So, on average, how many OEP interns are there each year? Is it A, 100 to 200, B, 300 to 400, C, 500 to 600, or D, 700 to 800?
It's A, 100 to 200?
That is incorrect.
It's B, 300 to 400.
That is also incorrect. One more.
C.
C is also incorrect. The correct answer is OEP holds appointments for between 700 and 800 interns a year. I know. As a reminder, the summer 2024 SULI and CCI applications are open, so if you would like to be a mentor, please let us know. Okay, last but not least, our final holiday trivia question. What is the name of the traditional warm holiday beverage that's made from mulled wine or cider, orange, cinnamon, and other spices? Is it A, hot toddy, B, eggnog, C, coquito, or D, wassail? We had a lot of food-based questions.
D.
Did you say D? D. Wassail is correct. Going out with a bang. At this time, this concludes our competition. Please let's have a round of applause for all of our contestants once more. So voting for the People's Choice winner is now open. You can either scan the QR code on the screen or the one on the agenda that you were provided when you came in. To make your selection, you will need to log in to make your selection, and you may only vote once. Voting will close today at 2:50 p.m. At this time, we would like to invite you to a reception in the lobby while the judges deliberate. And please, you're welcome to join us back here at 3 p.m. for the award ceremony. Thank you again.